Okay, so let's start my talk. So we give a talk on the application of optical frequency comb for fluorescence microscopy, featuring scanless fluorescence lifetime imaging. Go to background. So the fluorescence microscopy has been widely used in the field of bioimaging. So the most simple fluorescence microscopy is based on the fluorescence intensity like here. So it has an advantage of a simple setup, fast imaging, and high spatial resolution. However, it has some limitation. For example, the fluorescence intensity is sensitive to the photobleaching, and also it varies with dye concentration or excitation power. This results in a poor quantification. Another type of fluorescence microscopy is based on the spectral imaging, like here. It enables a multicolor imaging, like here, and distinguish the different fluorophore. However, it also has some limitation. The spectral overlap limits accuracy and requires a complex mixing. Also, the image acquisition rate is slower than the intensity-based method. In this way, this type of fluorescence microscopy has a fundamental challenge in sensitivity, specificity, and quantification. So third type of fluorescence microscopy is a fluorescence lifetime microscopy or FLIM. So the left shows what is the fluorescence lifetime. So when a sample is excited by a pulse light, the resulting fluorescence shows a time decay curve like here. So this decay curve is given by this equation where the tau is a fluorescence lifetime. The fluorescence lifetime tells us how long the molecules stay in the excitation state before emitting a light. So that this information so the such so the so in this case, the fluorescence lifetime gives the important uh, information of the molecule and its surrounding. So the one of the key feature is in film is high robustness to the experimental condition because the fluorescence lifetime is not affected by a dye concentration or excitation power. Also, the lifetime is sensitive to the microenvironment such as the pH, temperature, ion concentration, and so on. Furthermore, so if the endogenous fluorophore such as NADH or FAD is used as the image contrast mechanism, the label-free imaging can be possible. And another key feature of the film is the discrimination of spectrally overlapping fluorophore. So the lifetime contrast allows the separation even when the spectral overlap. Bottom left shows an example of such a discrimination for the two different kinds of fluorescence beads with a similar spectra and a different lifetime. So in the spectral image, so most of the spectra are overlapped to each other, so it is difficult to separate them like here. However, if we use a lifetime, if we of use a lifetime image, so we can easily separate them based on the signal analysis of the fluorescence lifetime. So in this way, the film gives a unique feature in fluorescence microscopy. So the straightforward film is a time domain film using a pulse light. The time domain film can be classified in two approaches. One is a laser scanning film by time correlated single photon counting or TCSPC. So it has a high sensitivity in this photon counting level and high time resolution in a few tens picosecond. However, imaging rate is limited to several FPS due to the slow TCSPC and the mechanical scanning of focal spot. The other is a full field film by a time resolved camera or time gated camera, like here. In this case, a high imaging rate can be achieved due to the full-field imaging with the camera. However, the time resolution is limited to a few nanoseconds due to the gate time of camera. In this way, the simultaneous achievement of high imaging rate and high time resolution is still difficult in time domain film. Another type of film is a phase modulation film or PM film. The PM film is based on the temporal response of fluorescence to the sinusoidal excitation like here. So when a sample is excited by an amplitude modulated to light at modulation frequency of B, the resulting fluorescence is also amplitude modulated in the same frequency of F. Right shows a comparison of the temporal waveform between excitation rate and fluorescence. Although they are in synchronized with each other, but there are some time delay between them due to the fluorescence lifetime process. So the time delay, so the phase delay of phi is related with a fluorescence lifetime using this equation. Therefore, we can determine the fluorescence lifetime by measuring the phi and b. So such a PM film has advantage of real-time point measurement, high precision measurement, and no requirement for fast detection system. However, since the usual PM film is based on the point-to-point measurement, it still requires a mechanical scanning of focal spot for 2D image. So when comparing the time domain film and the PM film from the viewpoint of parallel measurement, PM film is more stable than the time domain film. So the key of parallelization in the PM film is spatially multiplexing. Next slide shows the principle of operation for the spatially multiplexed PM film. So if the PM film can be multiplexed by a 2D array of excitation spot having a different modulation frequency, and the resulting fluorescence signal is measured collectively by a single photodetector, the resulting image acquisition time is largely reduced without the need for camera. In this case, the 2D array of excitation spot Pi correspond to a different modulation frequency of excitation right Bi to have a one-to-one correspondence. So the resulting fluorescence. So when such a 2D array of excitation spot is used for the excitation of fluorescence, the resulting fluorescence is also spatially multiplexed with a different modulation frequency Bi. So the 2D array of fluorescence spots Pi correspond to the fluorescence modulation frequency Bi to have a one-to-one correspondence in the same manner as the excitation right. Now, so what happens if we collect the signal from this two-dimensional spot of fluorescence and excitation light using a point detector? The answer is here, which shows the frequency domain description of the detected electric signals in RF region. Left shows RF spectra of amplitude and phase for 2D array of excitation spot. Importantly, so their frequency multiplexed by Bi. So each mode pair of amplitude and phase at the modulation frequency Bi correspond to the 2D array of excitation spot Pi, having a one-to-one correspondence. Also, the right shows the RF spectra of the amplitude and phase for 2D array of fluorescence spot, and each model pair of amplitude and phase at the modulation frequency Bi correspond to the 2D array of fluorescence spot Pi, having a one-to-one correspondence. Again, therefore, so we can reconstruct the image from these frequency multiplex signal So the amplitude ratio and phase delay between the excitation rate and the fluorescence at the each modulation frequency BI gives the fluorescence intensity image and the lifetime image at the each spot PI. So to achieve this spatially multiplex frame, we focus on the optical frequency COM or OFC. OFC is composed of a series of frequency spikes regularly separated by a constant frequency, like here. Based on the coherent link of frequency between the optical and the electric region, the OFC has been widely used for the optical frequency ruler or frequency gear. However, here we focus on a new feature of OFC, namely an optical carrier with a large number of discrete channels. To apply this feature of OFC for the spatially multiplex PM film, so there are two keys. So the first key is the 2D spectral mapping of OFC. So when the OFC is fed into the 2D spectral disperser, each OFC mode is separated at a different solid angle, depending on the wavelength. This is corresponding to the 2D spectral graph. So with a combination of 2D spectral disperser and a relay range system, this 2D spectral graph is transferred onto the sample surface as a 2D array of focal spot. Importantly, so the one-to-one correspondence is established between the OFC mode and the image pixel. So in this way, the wavelength to space conversion was achieved. So the 2D spectral disperser is achieved by a combination of the virtually imaged phase array or Viper and grating. So the Viper here, so Viper is a tilted Fabry-Pellot étalon, like here, having a highly reflective coating on both sides. One is fully reflective and the other is highly reflective. When the light is incident into the Viper, the total number of internal reflection is different along the vertical direction. In this case, the output light from the Viper has a different wavefront depending on the vertical position like here. And this wavefront is steeply tilted. This results in the large dispersion power of Viper comparing with the grating. Next, we consider the optical spectra of the output light at each vertical position of the optical Fourier plane. For example, at the bottom vertical position, the optical spectrum like here showing the multiple resonance transmission peak appears with a constant frequency spacing equal to FSR, so which is a similar spectra of the usual Fabry-Pellot étalon. However, such a resonance transmission spectrum slightly shifted depending on the vertical position, like here. Without the change of FSR, like here. So due to the steeply tilted virtual wavefront, like here. So to separate these spatially overlapped multiple transmission peak along the horizontal direction, we further use diffraction grating. As a result, these multiple transmission peak separately appears in 2D space. So this is corresponding to the 2D spectral graph, and the wavelength direction is developed as a zigzag line like here from shorter wavelengths to longer wavelengths. So the second key is the 2D spectral mapping of dual cone optical beat. This slide shows the behavior of the spectral domain and the spatial domain for when a pair of OFC is fed into the 2D spectral disperser. We prepare a pair of OFC with a slightly different FREP for dual-com optical beating. OFC1 with FREP1 and OFC2 with FREP2 and have such an optical spectra like here in the spectral domain. In spatial domain, the OFC1 is spatially overlapped with the OFC2, and then the combined OFC1 and the OFC2 is fed into the 2D spectral disperser. So each mode of OFC1 and OFC2 are separated at the different solid angle and make the 2D spectral graph on the sample surface as a 2D array of the focal spot. Here, so the solid circle and the dashed circle are corresponding to the 2D array of focal spot in OFC1 and OFC2 respectively. And the optical frequency of the OFC1 and OFC2 are close to each other. A group of optical bit signal is generated on the overlap area indicated by a purple color like here. So in spectral domain, a group of optical bit signal is generated between the adjacent mode via the multi-frequency heterodyning, and the secondary frequency comb appear in RF region. So this is a dual optical comb RF bit. Importantly, so that this bit signal is frequency multiplexed by BI, and frequency spacing is equal to delta FREP. So in this way, the one-to-one correspondence is established between the overlapped spot area and the dual optical comb RF bit. In other words, RF multiplexing of the excitation light is achieved in frequency domain and image domain. Therefore, they can be used for the 2D array of excitation spot having a different modulation frequency. Next slide shows the experimental setup and the sample. So we use a pair of fiber OFC at the 1.5 micrometer as the OFC1 and OFC2. Specification of OFC1 and OFC2 is here. So both OFC has a frequency spacing around 100 megahertz, and the frequency difference between them, or delta FREP, is around 1 kilohertz. So the fundamental light from the OFC, both OFC were converted into the THG light at 520 nanometer by a pipeline crystal. Optical spectra of the green OFC light is here, so the corresponding power, optical power, is around the 10 milliwatt. So their green OFC are spatially overlapped and then fed into the combination of Viper, grating, and the relay lens for the 2D spectral dispersal. This results in the forming of 2D array of the excitation spot on the sample surface. Here, the sample used here is a combination of a test target with a chamber of fluorescence solution. So when the excitation light comes to the sample, so the test pattern image fluorescence appeared. So this fluorescence image was detected collectively by a photomultiplier. Also, a part, the PMT2, also the part of the excitation light was detected by another PMT, so PMT1. So temporal waveform of the detected RF signal from the both PM photomultipliers was acquired by a first digitizer. So we first verify the one-to-one correspondence among the focus, optical spectrum, and RF spectrum. We perform the spatial sampling of 2D excitation spot using optical fiber with a core diameter of 10 micrometer. We scan the position of the fiber across the 2D array of excitation spot. Here, so you can see the typical result from two positions. So one is top left uh, here, and the other is bottom right here. The optical spectra obtained at each position shows a clear spatial dependence, like here and here. And these are the temporal waveform of RF beat measured and the RF beat signal and the Fourier transforms RF spectrum like here, with the frequency range from 0 to 550 megahertz, 0 to 50 megahertz. Each position of the RF spectrum has a different bit frequency. Also, their RF spectra are replica of the optical spectrum to have a one-to-one correspondence. In this way, that we confirm the one-to-one correspondence among the focus, optical spectrum, and RF spectrum. We next demonstrated the scanless imaging of fluorescence intensity and lifetime. We use a rhodamin 6G aqueous solution having an emission wavelength around 543 to 617 nanometer and a lifetime of 4.08 nanosecond. Left shows the temporal waveform of fluorescence RF signal. So we can clearly confirm the burst signal in the center position. Fourier transform of this temporal waveform gives the amplitude and phase spectrum of the fluorescence RF beat, like here. So their frequency multiplex signal, including a 44,400 mode. So this number is corresponding to the total number of image pixels in the constructed image. So the spectral modulation of the spectral envelope reflects the image information of fluorescence intensity and lifetime. We also measure the similar signal for the excitation rate for the reference. Then we calculate the amplitude ratio spectrum of fluorescence to the excitation rate. And based on the one-to-one correspondence between the RF frequency and the image pixel, the fluorescence intensity image is reconstructed like here. Similarly, so after the phase difference spectrum between the fluorescence and excitation rate is calculated, fluorescence phase delay image is reconstructed like here. Then, so that this fluorescence phase delay image is converted into the fluorescence lifetime image based on this equation. So the test pattern was clearly confirmed in these three images. However, the image contrast mechanism is different among them. So the fluorescence intensity, fluorescence phase delay, and fluorescence lifetime. So the lifetime image of value of this image are in good agreement with the literature value of this sample. We next investigated the dependence of the image SNR on the number of the accumulated image. Left shows a comparison of fluorescence intensity image with respect to the different number of accumulated image. So 100, 1,000, 10,000, and 100,000, which are corresponding to the image acquisition time of 100 millisecond, 1 second, 10 second, and 100 second respectively. The image contrast is improved by increased number of the image accumulation. Right shows the image SNR with respect to the number of signal accumulation and corresponding data acquisition time. The image SNR is linearly increased depending on the square root of the number of accumulating signal or the data acquisition time, indicating the short noise limit measurement is achieved. Finally, so to evaluate the quantitativeness of the fluorescence lifetime measurement, we perform the film imaging of four samples with a different fluorescence lifetime. 4.1 nanosecond for the sample A, 1.8 nanosecond for sample B, 2.4 nanosecond for sample C, and 3.0 nanosecond for the sample D. Although this film image shows the same pattern of test chart, their lifetime value are different among them. Right shows the relationship of the fluorescence lifetime between the literature value and the measured value for these four samples. So when the accuracy of fluorescence lifetime measurement is defined as the root mean square error between them, the accuracy was achieved to the 0.07 nanosecond. Finally, so we summarize the present talk using this slide. So we demonstrated the spatially multiplex PM film based on the 2D spectral mapping and frequency multiplexing of the dual-comb optical beat. So the scanless imaging is achieved at the maximum acquisition rate equal to delta f-rep or 978 Hz. And the measurement accuracy of fluorescence lifetime was determined to be 0.0 nanosecond. Thank you for your kind attention.